Each day of our life, we wake up, we wash ourselves, have a little breakfast, and we commute to our job. If it's a sunny day, a wonderful blue sky will make us feel ready to go out and start to work. Otherwise, if it's raining but the sun is visible, it's possible to notice a breathtaking rainbow that will fill us with joy and amusement. Later on, after an entire day in our office, we return home, and if it's a special occasion, we might have a nice aperitif with our loved one in one of those romantic places with a stunning view on the city. We'll rest from the hard day and enjoy the time by seeing a wonderful sunset. Some of us will probably prefer to go out after dinner and reach the top of a hill away from the city in order to have a magical night watching the stars with their partner in the night dark sky. But do we ever ask ourselves why the sky changes color throughout the day, starting blue, becoming red, and getting dark at night? And why a rainbow forms only if it's raining? If you want to know more about this, follow me in this video, a fantastic journey through some of the ordinary but surprising optic fun facts. Before diving in the explanation of these common phenomena, we need to take a step back and try to answer a fundamental question: what is light? The main science that studies this topic is optic, which was firstly developed by Isaac Newton in the 19th century. At that time, everyone thought that light was a wave, characterized by its own wavelength, the distance between two successive peaks, frequency, and intensity, the height of the peaks. The main behaviors of light, which were studied in that period, were two: reflection and refraction. The first one happens when a ray goes against a reflective material like a mirror that doesn't let anything pass through and reflects the ray with the same angle of incidence. The second phenomena is typical of those surfaces that are not totally reflective. When light passes from a material to another, it changes trajectory. The deviation is proportional to the difference in density between the two areas. Have you ever seen what happens if you point a laser on a glass of water? The beam bends in a different direction when it enters in the fluid. Later on, in the 19th century, with the contribution of the famous James Clerk Maxwell, physicists discovered that light is just a type of electromagnetic radiation with a particular range of wavelengths that is visible by our eyes, between 300 and 700 nanometers. As a matter of fact, light just physically differs from an X-ray, gamma ray, or infrared in the value of wavelength. These types of radiation undergo the same effects of reflection and refraction. As an example, sun rays appear white because they're equally composed of each possible visible wavelength, whereas special lamps illuminated with sodium are characterized by an orange light due to the fact that emission is mainly made up of some types of wavelength around 600 nanometers. Moreover, thanks to the development of advanced mathematical tools, scientists were able in the last 50 years of the 19th century to explain in a more rigorous way a wider range of luminous phenomena. They understood that light has a different angle of refraction depending on its wavelength. By knowing this, scientists were able to explain some effects that were observed by older physicists like Newton. One of them is particularly famous. Do you know what is the worldwide known symbol of Pink Floyd? The prism. And why is it important? The prism has the ability of separating different wavelengths of a luminous ray. How does it manage to do that? The beam pointed on the prism undergoes a first refraction when it enters in the glass and a second one when it returns in the air. Due to this double refraction, all the different colors take slightly different paths in space. The components of the original light are separated in what we call as spectrum. Did you know that a similar phenomena is responsible for those marvelous rainbows you see after a rainy afternoon? Do you know how that event can be explained? The answer may be surprising. Before finding out more about this, be sure to like or dislike the video so that we can continue to improve and make these videos better for you, the viewer. Plus, be sure to subscribe to the channel, clicking the bell so that you don't miss any of our weekly videos. In order to solve this problem, we must ask ourselves this question: what are the two major requirements for the appearance of a rainbow? Sun and rain. This is our starting point. As a matter of fact, the solution is already contained in those two words. Let's start from the first one. What is rain made of? Water. And how can we sketch the rainwater? We can't imagine it as a collection of spheres with different sizes. Now we can consider the second feature that characterizes the formation of a rainbow: sunlight. When a beam of sun rays hits a sphere of water, it undergoes a first refraction, a second reflection on the back of the droplet, and a final refraction when getting out. As a result of this process, light is diffused like a prism. Since the droplets are in different positions, the rays will come out in various directions. So when we consider rain as composed by a huge amount of water droplets, the final effect is the separation of sunlight in its different colors, the rainbow. In addition, a similar effect can be observed thanks to another different material. Have you ever seen something strange while filling up your car at the refueling station? If some spots of oil are hit by a sun ray, they produce a little rainbow due to the same diffusion. To go on with other everyday fun facts, we must define a new phenomena: scattering. With the beginning of the 20th century, scientists discovered that light was quantized in the form of small particles called photons. Suddenly, they started to doubt about the wave appearance of light, approaching a more corpuscular description. Therefore, with the development of quantum mechanics, a model that is able to describe particles better than any other theory, physicists found out that each particle has an undulating behavior. In conclusion, we can say that light can be treated both as a particle or as a wave depending on the different situations. Thanks to this theory, scientists were able to describe the interaction of single atoms with radiation. This particular phenomenon is also known like scattering. The outcomes of the interaction depend on the size of the atom compared to the characteristics of the wave. Shortly, the atom absorbs light and re-irradiates it, emitting new photons. Firstly, if we have a particle much smaller than the wavelength of the radiation, we call it Rayleigh scattering, which is named after the 19th century British physicist Lord Rayleigh. It is possible to find that the power of light diffusion is proportional to the inverse of lambda to the fourth power. As a consequence of that, blue, which has a smaller wavelength of 500 to 520 nanometers, is reflected much more strongly than red, which has a greater wavelength of 700 nanometers. This is the main reason why our sky happens to be blue, as the particles in our atmosphere interact according to Rayleigh scattering. This demonstration might have satisfied your answer, but an accurate viewer won't be totally okay with these statements and will remain skeptical. As a matter of fact, a single question seems to destroy this description. Do you know it? Here it is. Why is sunset red? Air is always the same and behaves according to Rayleigh laws, but there isn't any trace of blue. Why is it like that? The answer is really simple. When the sun is setting at the end of the day, it appears in front of us and its light will have to pass through a greater layer of atmosphere than at midday. Since blue and green components are emitted with a higher power, they are consumed after a certain distance traveled in air, and only the other colors like red, purple, and orange remain visible. Going on with this topic, further questions might rise about the sky. For example, why is night sky dark? Where has our atmosphere gone? Atmosphere is transparent when the sun doesn't lighten it up. Let me try to give you an easy example. Have you ever driven with fog? What happens when you open your headlights? Light interacts with water particles of the fog and undergoes a certain scattering. The beams are diffused and the fog obstructs our vision more than before. On the contrary, if our headlights are turned down, the fog seems to be less thick. The same happens on Earth at night. When the sun goes down, atmosphere is no more enlightened and becomes almost transparent, allowing the view of stars and of the dark background of space. The last but not the least effect that will make you feel totally shocked is suntan. Have you ever desired a beautiful tanned body in hot summer? Well, a lot of optics lays under this phenomena. Let's go through it. We have previously said that solar light is white because it's equally composed of all colors. Therefore, the sun is not just a source of electromagnetic visible radiation. As a matter of fact, it irradiates in other wavelengths such as infrared. Being hit by visible light has positive effects on our body, but the same can't be said for other frequencies of radiation that happen to be harmful for our organisms. Although the majority of them is totally absorbed by our atmosphere that acts as a shield which allows life on Earth, some dangerous rays might reach the ground. The most famous ones are UV rays. They can seriously damage our skin, causing sunburn. Fortunately, our body has a great protection against sunlight, which is called melanin. It is a natural pigment that has the ability to absorb a certain amount of UV rays, and it can have two different colorations. One is red, pheomelanin, and the other is brown, eumelanin. When sun hits our skin, the organism starts to produce melanin at a higher rate, reducing the risk of a sunburn. But how does melanin manage to give us that beautiful tan we love to show at the beach? There are two main processes. The first one is oxidation of melanin that makes its color turn darker and darker. In this case, we don't have a greater protection from future UV rays, even if we are totally tanned. We should still use sun cream. On the other hand, a different way of getting tanned is possible. If the majority of the rays is UVB, our body creates an excess of melanin that causes delayed tanning, which is far more protective than the oxidation one. A skin tan due to this process may be able to sustain UV rays 3 times better than a normal one. In conclusion, we are surrounded by several phenomena that might appear ordinary and common, but secretly hide a lot of amazing physics effects. The majority of us has probably never thought about the origin of a rainbow or a breathtaking sunset. But trying to find a possible explanation for these events is what science is there for, and it will continue to make you feel surprised and astonished every single time. That's all for this video. Thanks for watching, everyone. Did you find this topic exciting? Are you amazed by the description of this fun everyday fact? Did you already know why the sky is blue or how a rainbow can form? Have you ever heard about scattering before? Is there anything more you want to hear about optics? Let us know in the comments below. Be sure to subscribe, and I'll see you next time on the channel.